for a long time, it was really the preferred model. It's very flexible. You can solve a lot of problems with, but it does not scale so well when you have very large data sets, and then the computation takes too long, and so it is not for billions of data points. It just doesn't. You just can't do it. But it's a very, very nice idea, and it's for small data sets. It's absolutely great. So let's look at a somewhat complicated data set here. So you can see this is definitely not linearly separable. That this is you can't find a line that separates these two, the purple and the yellow things here. So we can try logistic regression. So here is this code I have uploaded. You can look at this code. So the piece here is sort of a way to visualize this decision boundary. So the one that separates the +1s and the -1 labels. So the model is going to predict points having a label +1 and other points have predict -1. And this code here is going to sort of show where it separates the 2 points. So let's run this logistic regression on this data set here and see where it separates the two, the +1s and the -1s. So you can see here that it misclassifies quite a few points here, right? So we have these. So the purple area here, that should be the ones that have all the yellow or orange points in it, and the other ones should be on the blue point should be on the other side. But you can see here there are a number of points here that are misclassified. These yellow points here, they belong down here, and these blue points here, they belong up here. So but that's just because, of course, it can't be separated by a line. But the logistic regression tries to do the best it can. And so let's try to figure out how well it does and see how well it does how well it separates the data set here. And we can see that if we run these metrics here, so these are part of the sklearn metrics as an accuracy score and a confusion matrix. We haven't discussed confusion matrix, but I'll do that another time. The accuracy score, well, it simply looks at how big a percentage of the data points are correctly classified by the model. And so it correctly classifies 89.5% of the data points. So that's maybe you think is pretty good, but actually it's terrible. So that's not good. So when you're using these things, you really want much better. Yeah, so it's just the accuracy score compares the. So now let's try this more advanced thing, the support vector machine. And I'm going to use a support vector machine with a radial basis function that we don't know what that is, but we'll see what it does later on. But it's a way to, again, a classification algorithm, and again you can use the code here. And again, I have this code here, which gives us the decision boundary. It shows how it separates the points. So let's see what that does. So here is the separation boundary for a support vector machines with an RBF kernel. That, as you can see, is not a line anymore, and it does pretty well separating the point. We can't separate it completely without really overfitting. We probably could get a by sort of tweaking the parameters in the RBF in the support vector machine, what's called a kernel. We could probably get it to separate these almost perfectly, but that would be total overfitting also. But let's see how well it does in separating these, and we can see it does about 5% better. So it's well, 5% maybe you think that's not so much, but it's actually huge. It correctly classifies 94.5%. So that's a much better thing. So what is this support vector machines? Well, it's as I said, it's a very, very elegant model. And we'll start with describing what a linear support vector machine is. And a linear support vector machine, that will also create a separation line. And so here is a linear SVM, and see how well that separates. That does about as well as the logistic regression, but it's, as we'll see later, much more flexible in terms of generating much more complicated decision boundaries. So what is this? What is this support vector machine? How does it work? Here is the code for the linear support vector machine. We can see the accuracy score is better than the logistic regression. It's 86.5%, but of course not as good as a one with the RBF kernel. So the principle in the support vector machine is to find the best, in some sense, line that separates the data. And so here I have my data set here. I have the -1s are red, the +1s are green, and I have 3 lines that separates them. So which one is the best line? I could make that a quiz, but I didn't. But I think we can somehow agree that it's. Well, what would you say would be the best line?
I would say my vote is for green line.
Yeah. Okay. Mine too. And why is that?
I would say because it is very cleanly separating the green points from the red points without touching any point very closely. So even if there are like more data points around that point, it will still separate well.
Right. That's right. Yeah. See, the thing is that you can sort of put a band around this. I think it's in the next line. You can put a band around this green line where there's no data points, right? You can put a belt around it, and so that there are no data points inside this belt, and so that's the widest belt you can put around. You can put a belt around this yellow one here, but that'll be very, very narrow, right? It'll be very close to the lines itself. So there will be a.
Is it more precise to say that the green line is the one that maximizes the perpendicular distance of all the points to it?
It's the one that maximizes the distance to the closest points.
Oh, just the closest ones.
Yeah. So yeah, it's just the closest. So that's actually the idea. We're going to try to find this line that has a property that this band around it is as wide as possible. It means that the distance to the closest data point is maximal. So for instance here, what's the distance to the closest data point? Well, that's this little distance here. The distance from the green to the closest data point, well, that's this distance here. So you see, that's bigger than for the yellow one. The same thing for the green one here. The distance to the closest data point is this thing here, but again, that's smaller than for the green line. So the green line is in that sense the best separation. So the idea here is again to look at the distance to the closest point. And so it's sort of the line, the best line is gonna be right in the middle of these closest points here. So here we have a point here that looks like I have more or less pretty much the same distance as this one. So the line here will sort of be right in the middle of these closest points. And that has to be expressed mathematically. And one can do this in a somewhat complicated way. But let's. I don't want to. I think Adam has quite a bit of material, so I'm not going to go through the whole thing here. But let me maybe go up to the board and try to explain a little bit what we're doing here. So I'm going to not stop sharing and show the. So can you make my picture big, Manish?
Yeah, I can see your board. Yeah.
Yeah, but I can't see. Can you? Is it big?
Yeah, it's big. Correct. Let me pin your video so that's big. Yes, now it's perfect.
Great. Yeah. So I made this drawing here on the board here, and so this is pretty much the same as what's in the note here. So here we have this distance here to the closest point. Here we have another one of the points that are closest.